Mitchell, what does frequency mean? Yeah, the physics definition of frequency, yeah. I'm sorry? Can you say again? No, but you're close. Anybody help him out there? Mitch just said frequency is the time that it takes to go around a cycle or around a circle once. That's not frequency, that's the period. So you got a definition, you just get the wrong definition, that's all. The time that it takes to go around the circle once, which would mean we could provide an equation for period, time over the number of evolutions, or in general, the number of cycles. All right. Well, that saves me one question later on. Okay, you just nailed the second one that I was going to ask. What's frequency mean? If period is a time for one revolution or one cycle, then frequency is, Merrick? Good. It's the number of cycles per unit of time. So it's going to be the exact opposite of period, number of cycles over time. Now, this equation, neither one of these equations actually is on your data sheet. They're more just definitions as opposed to equations. However, we're still going to need to use them from time to time as equations to solve for frequency or period. How do we relate these two together? These two definitions, frequency, period, together. What's the equation that does appear on our data sheet that ties them both together? Q? You can check your data sheet if you forget, as long as you can find it, that's all. Good. T is equal to 1 over F. The period is equal to 1 over the frequency, which, of course, is on our data sheet. Hey, what units would frequency be measured in? Frequency is measured in cycles per second, right? But we abbreviate that sometimes with an HZ, which stands for a hertz. What about period? Seconds per cycle, or sometimes we just say it, usually we just say it as seconds. Good? One more equation. Relates to a third term we learned the other day, speed. We don't really need to define speed. We know what that means. The equation for speed is distance over time. Hey, we're using distance over time. We talked the last couple of days about a centripetal acceleration. The object going in a circle is experiencing an acceleration, but yet we're describing it by the equation V equals d over t. It's moving at a constant speed. It's a group A equation. How can we say it has an acceleration if the speed isn't changing? What's happening? What's the deal with that, Zach? Okay, so the speed isn't changing, but the direction is changing. Okay, now acceleration isn't dependent upon the change in speed, it's dependent upon the change in velocity, which includes direction. All right, back to this equation. The distance around the circle once is known as the, what's the word? It starts with a C. No? Circumference, good. And what's the equation for circumference? There's two of them, but usually we write it as one of the versions. Good, 2 pi r, or you could say pi times d, pi times the diameter. And that's the distance around the circle once. Alice, what's the time around the circle once? Good, the period, big T. Now the units for that, of course, would be meters per second. We'll square that off in red as well because that one appears on my data sheet as well. Hey, quickly, frequency, vector or scalar? Is there a direction with it? Scalar. Period, vector or scalar? What about speed, vector or scalar? Scalar, good. All right, two more terms. Centripetal acceleration and centripetal force. What does the word centripetal mean? In the context of acceleration or in the context of force, centripetal means what? Center seeking, right? It's trying to get to the center of the circle. The centripetal acceleration is the acceleration that's directed toward the center of the circle. We talked about this just a minute ago. We can have an acceleration even when the speed isn't changing because the direction is changing. Now, it's kind of weird that the acceleration is toward the center of the circle when the velocity is never toward the center of the circle, right? the velocity is always a tangent to the circle. It's never toward the center. But the change in velocity is toward the center of the circle. Therefore, the acceleration is toward the center of the circle. A little bit easier to understand for force, though, I think. The centripetal force is m times v squared over r. Okay, we did a little demonstration the last couple of days to show you why centripetal force is toward the center. Swing the keys around my head. What supplies the centripetal force? Always something, right? Never a fundamental force. Centripetal force always has to be caused by something. In this case, it's caused by, Adam? Yeah, force, but what force? What's causing this thing to stay in a circle? Thumb? My hand. My hand's supplying it. Where is my hand? In the middle of the circle. I'm applying a force toward the center of the circle. We call it a centripetal force. If the force is toward the center, then the acceleration is toward the center as well. Units, meters per second squared, in newtons, vector or scalar? No, it's a vector. So is this. Now, vectors have direction, right? The centripetal acceleration has a direction toward the center of the circle. Now, this equation isn't going to tell me which direction it's going in, but that's okay because I just know it's going toward the center of the circle. They're both vectors. Just understand that these equations will only give us the magnitude of the acceleration, the magnitude of the force, not magnitude and direction. Has a direction, we just don't get it from the equation, that's all. Good? Make sense? One final thing. We alluded to this earlier. We know that centripetal force is not fundamental. It's got to be caused by something. The Earth going around the sun, there's a centripetal force that's caused by gravity. The electron going around the nucleus, for those of you who take chemistry, the centripetal force on the electron is caused by an electric force. Case of a car going around a turn, the centripetal force is caused by the frictional force between the tires and the road. If it's caused by something, then we can set the centripetal force equal to that something. And sometimes that's helpful to us. Now, we did an example problem yesterday involving centripetal force and frictional force. That doesn't mean that we can't go back to this. Just mv squared over r. We can. But if it doesn't work for us, then it might be useful to set two forces equal to each other because there's always something that is equal to the centripetal force. All right. We had 3 questions for homework yesterday that were based on this. They were on page 259 of your textbook. Any issues with any of those 3 questions, please? No? All right, let's take a look at number 2 then. Automotive manufacturers test the handling ability of new car design by driving a prototype on a test track in a large circle with a radius of 100 meters at ever-increasing speeds until the car begins to skid. A prototype car with a mass of 1,200 kilograms is tested and found to start skidding at a speed of 95 kilometers per hour, which, I want to circle that, right? Because we want to convert it to meters per second. What's the coefficient of friction between the car tires and the track? Here's the radius for number 2. Here's the mass. Here's the speed, 95 kilometers per hour. We know how to convert that to meters per second, right? Multiply it by 1,000, divide it by 3,600. What does that work out to be? .38 meters per second. Thank you. Well, in this case, I think it's fairly clear that we're going to, Adam, set the centripetal force equal to that force of friction. Fc is equal to Ff. Yeah, but the normal force here, mu times the normal force of friction, the normal force here, flat horizontal surface, is going to be m times g. M's cancel, meaning it doesn't really matter that the car was 1,200 kilograms. the speed, take the r up by multiplying, speed is equal to the square root of mu times g times r. Mu is, oh wait, what are we looking for? We're looking for mu, right? So we're going to say mu is equal to v squared over r times g. The g goes down by dividing instead. So what do we got here? A speed of 26.38 squared divided by r, 100 meters, times 9.81. You do the math there, and it should work out to be 0.710. And there are no units, remember, associated with coefficient of friction. Good? Is that okay? Any others? Okay, yesterday we finished off with a little bit of analysis on centrifugal force. We watched a video, Cirque du Soleil video, where we saw a guy was in a circle going to the outside of the circle, but we could see how he wasn't being pushed to the outside of a circle. Rather, it was his inertia that was taking him in a straight line towards the outside of the circle. We talk about centrifugal force, and we put the word centrifugal in quotation marks. How come? Why is it not? I mean, we talk about centripetal. It's not in quotation marks. Why is centrifugal in quotation marks? Yeah, it's a pseudo force, a force that doesn't really exist. It's not there. Centrifugal force is the force that pushes you out towards the outside. We'll say the outward force, the force that pushes you away from the center. I'm putting force in quotation marks here because it's not really a force. I'm going to draw a picture to explain to you how we know that it's not a force. What's really happening as you get pushed to the outside of a circle. Okay, here's the circle. Maybe it's a merry-go-round. When I was a kid on the playground at my elementary school, there was a merry-go-round. You don't see merry-go-rounds anymore. You know why you don't see merry-go-rounds? Because guys put their motorcycle wheels against it and get them going a million miles an hour. I didn't do that when I was a kid. This merry-go-round is spinning clockwise here on its axis right there. Okay, let's say that I'm halfway between the center of this merry-go-round and the outside. This point X is a certain marked point on this merry-go-round. The merry-go-round at my elementary school when I was a kid had a nick in one of the handles, a big nick in one of the handles. And for whatever reason, nobody ever wanted that one. Okay, everybody would fight to get one of the other handles on this merry-go-round. Nobody ever wanted that bar. Nobody ever wanted to hold onto the bar with the nick. I don't know what it was, but when my brother went through that school 3 years before me, when I went through that school, nobody would touch that bar with the nick. Okay, I'm on it. Okay, this is the bar with the nick. There's the little nick at the end of it. Okay, now what happens? As I spin around faster and faster and faster, the guy in green there, the guy dressed St. Patrick's Day, I guess, got a green shirt on, let's say. I feel like I'm being pushed to the outside. Am I? No, I'm not. What happens to me? Well, as this thing spins clockwise, I go in a straight line. This is what happens to me. I go in a straight line. Now, by the time I go in a straight line far enough to kind of get over that far, this bar with a nick in it has come around to catch me. So I end up going to the same place as I thought I was when I felt like I was being pushed out. It's just I didn't get there by being pushed out. I got there by going in a straight line. Now, what happens in between? Here's the bar. Maybe a tenth of a second after this moment in time, where am I? I'm right here, right? Where's the bar with the nick? Right here. I'm still on the bar. I'm going in a straight line, but I'm still on the bar. but I'm a little bit closer to the edge now. A little bit later, maybe another 1/10 of a second later. Where am I? Oh, I'm over here now, going in a straight line. Where's the nick in the bar? Right there. Where am I relative to the bar? I'm still on the bar, but I'm closer to the edge now. A little bit later in time, where am I? I'm right here now. I'm right out at the edge where the nick was. I'm still on the bar. I'm on the end of the bar. I've stayed on the bar. It felt like I was being pushed out the bar from the middle right here to the outer part of the bar here, right at the end. I wasn't being pushed. I went in a straight line the whole time. It just felt to me as if I was being pushed outwards because I was going in a straight line. So what's really the cause of this pseudo force that we call centrifugal force? One word. It's an I word. What's happening to me right there? I'm going in a straight line. I always want to go in a straight line. What do we call that? Yeah. It's inertia. Yeah. Centrifugal force isn't a force. Centrifugal force is what we perceive as a force, but is really just our inertia carrying us in a straight line. Does that make some sense? Remember the video we saw yesterday, Cirque du Soleil video? Guy was going around in a circle, jumps off of the side. Okay, he's in the middle. Where does he go? Well, he ends up going to the edge. But how does he get to the edge? He's not forced to the edge, right? You could see clearly that he was going in a straight line to the edge of that. From his perspective, he felt like he was going outwards. He felt like he was being pushed out to the circle because the red X, if there was a red X on it, would have been kind of keeping up with him as he was going in a straight line towards the outside. Good? And I'm going to